about a year from now, when I actually know something and don't just have numerical conjectures. But since one of the themes of this workshop is computation, and since that's all I really have so far, I think in that ways it may be more suitable for now than a year from now. It's also going to be very much a talk in the sense that I haven't prepared illustrations. So the subject is very geometrical. It's a trimer model. And in some ways, the most natural trimer model you could have in a three-colored hexagonal grid, or maybe I should say triangular grid, where you've got, the usual arrangement of six vertices around one, and you can consider trimers consisting of three consecutive nodes connected by edges, and you could try and fill a region up, some finite region, or the infinite plane. But I'm a combinatorialist, so I don't want to count tilings of the infinite plane because I already know how many of them there are. There are infinitely many. But you can get interesting questions by restricting to a suitable subdomain of such a grid and counting those configurations. And that's the kind of result I'm going to talk about today. I think it's very exciting because a lot of the techniques I know for solving dimer problems simply don't apply directly in the trimer world. But it is surprising that you can find conjectural exact formulas that are reminiscent of the sort of things you see for dimers. So I think this will be a great challenge for the combinatorial community to take existing tools and to extend them in new and unsuspected directions, motivated by these intriguing formulas. So I'm going to start with a bit of a review about dimer models and Aztec diamonds, which I hope for many of you will be review. I hope it'll be comprehensible to those of you for whom it isn't a review. And then I'll talk about the work of Conway and Lagarias, who got these intriguing results for trimer models. And then I'll talk about how to sort of combine these two branches to try and find things that, like Aztec diamonds, exhibit beautiful exact formulas, but also are really about trimers, the way Conway and Lagarias' work is. I should say, by the way, that I've had about an hour to prepare this talk because I only read the email inviting me to give this talk 2 hours ago. And so I apologize in advance for any roughness. Hopefully the freshness will compensate you for the rushedness. Also, I should say, if I am speaking too quickly, please slow me down because the adrenaline that I'm on right now might cause me to speak too quickly. And I know many, if not most of you, are native French speakers, and the average French mathematician speaks much better English than the average English-speaking mathematician speaks French, but I would still hate to go too fast. So someone in the text, please slow me down. In fact, someone has already said something in the chat. Yes, that's right. Yeah. But feel free to interrupt me aloud or in the chat. So anyway, I am also going to want to share my screen from my iPad. So let me try to do that. So there is a famous dimer model in the plane originally discovered by Benson, Carlson, and Zapp, if I have the names correctly. So they were looking at the square grid, and they looked at models that looked like this. So here's a graph with 12 vertices, and you can look at all the perfect matchings or all the dimer covers of it, and there are exactly 8 of them. That's 2 cubed, and this belongs to an infinite family of larger diamond-shaped subgraphs of the square grid, for which the number of perfect matchings is always given by 2 to the power of the nth triangle number. And this, as rediscovered by me and worked on by me and some other people, proved to be a very fruitful line of inquiry at the interface between combinatorics and physics, because unlike the ordinary square grid, which is a more natural shape to look at, whose dimer covers tend to be spatially homogeneous, when you use the kind of boundary conditions that are in this shape I showed before, called an Aztec diamond graph, there's this interesting phenomenon that there are different phases of the model throughout the bulk. And so this meant that on the one hand, the model was exactly solvable, But on the other hand, it was very phenomenologically rich and exhibited this really interesting phenomenon of a sharp boundary between the orderly region and the chaotic region, where you see a gradual modulation in local statistics in the chaotic region, whereas in the orderly region you just see a kind of trivial Gibbs state from the infinite model manifesting itself. So it took a lot of work by a lot of people to understand this, but I think we could all agree at this point it was worth investigating for dimer models. And examples of this, by the way, also come from the combinatorics of plane partitions, because a plane partition constrained to live inside a box can be understood also as a perfect matching of a hexagonal graph. So I'll just draw the kind of graph we're talking about. So here's a honeycomb graph. Chemists were interested in these also as benzenoid molecules, and you can count perfect matchings of these graphs as well, and they are given by nice exact product formulas. And one way you can recognize that there's going to be an exact formula even before you found it is that the sort of numbers you get when you count these regions, count the perfect matchings of these regions empirically, have very small prime factors, and that's a sort of clue that there's going to be a nice product formula. So any questions so far? Okay, so that's one strand of the background to my recent experimental work. The other strand is work done by Conway and Lagarias, applying combinatorial group theory to questions of the existence or non-existence of tilings of certain regions. So let me erase that. So let me draw the kind of region that Conway and Lagarias were studying. Now I should say, although this looks like a picture I drew in the last slide, the interpretation is very different, because before I was talking about perfect matchings of a graph, and so you can understand that there are 6 vertices bounding each of these hexagons, and in that picture I was looking at covering all the vertices of that graph by choosing a subset of the edges such that each vertex in the graph appears as an endpoint of exactly one of the selected edges. But that's not the game we're playing now. The game we're playing now is we're actually going to tile these regions using shapes made out of 3 hexagons. So if I replace each hexagon by a dot, and I draw an edge joining the dots representing 2 adjacent hexagons, I get a picture that looks like this. Okay. But now we're not looking at perfect matchings of the graph or perfect dimer covers. We're looking at perfect trimer covers. So for a graph that looks like this, let me see if my Apple Pencil's got a little bit of charge. Yes. This would be a trimer, and this would be a trimer. And so that would be an example of a perfect trimer cover of a graph like this. Now, Conway and Lagarias were not interested in counting, they were interested in existence, and by and large, they did not consider the mixed case, where you allow both those 3 in a line trimers and the triangular-shaped trimers. So they were looking at shapes that were like this, but larger, which they called triangles, and you could look at, trying to tile a triangle using smaller triangles of this size, specifically triangles that have just 3 vertices, or you could look at tilings of a large triangle using just the 3 in a line tiles. And using combinatorial group theory methods, they found an exact criterion for when a triangle of side length n, here my parameterization will be n is 3. So when can you tile a triangle of side length n by triangles of side length 2, an exact criterion for that? And when can you tile a triangle of side length n with trimers where the 3 dots are in a line, as in this tile? But they didn't count them when they exist, they just determined when they exist and when they don't. So I'm going to follow in their tradition, but I'm going to depart in 2 ways. First of all, I will allow admixtures of these 2 kinds of tiles. And second of all, I will be interested in enumeration and not just existence, although existence questions are also interesting. But I will not allow the other kind of trimer that you might think you would want to include in this game, which looks kind of like this. So that's another way you can take 3 dots in a triangular grid that are joined and tiled with them. I'm not going to allow this, but I will give it a name in a second. So I couldn't find in the literature standard names for these trimers. If I am mistaken, someone should please let me know. But if there is no standard name for them, I'm going to wear my recreational mathematician hat and give them names that rhyme with each other. So I'm going to call this a bone. And there's actually precedent for calling this a tribone, but I'm just going to call it a bone in the context where we already know we're talking about trimers. So that kind of trimer I'll call a bone. This kind of trimer I'll call a stone because it's nice and compact. And this kind that I'm not allowing I will call a phone because it looks a little bit like a flip phone that's been opened. I think it was Timothy Chow who suggested the name phone. Anyway, I'm going to be talking about tilings of various sorts of regions by bones and stones. But then the question becomes, what sort of region should we be looking at? Oh, I made a mistake. The correct graph should have a horizontal edge over here. Okay. So it's not always clear what the right shape to tile is if you're trying to find pretty exact formulas in combinatorics. Going back to dimer models, the most natural thing to try and cover with dominoes is a square. And there is a nice formula due to Temperley and Lieb and Fisher for the number of domino tilings of an n by n square where n is even, involving trig functions, and it's very nice in its way, but it's a little harder to guess the formula because you wouldn't necessarily see nice small prime factors coming when you do empirical work. So I'm not saying that there won't be interesting exact formulas for tilings of these sort of triangles grids T sub n, but we're not getting any clues as to their existence because when we do empirical enumerations, we just don't see nice patterns governing them. So one of the things I want to share is what is the right analog of an Aztec diamond for trimer models in this grid. So here I should pause and take stock of the time. The original email seemed to suggest I have until 50 minutes for this talk. Is that correct, or should I aim to go shorter? So should I aim to stop at 40 past or 30 minutes past, or all talks at 50 minutes? So I have until 40 past. Let me just check my watch and see where I'm at right now. Oh, I've got plenty of time. It's only 7 minutes past. Okay. So one feature of the Aztec diamond is that if you two-color the vertices in the sort of natural way so that every white vertex has black neighbors and every black vertex has white neighbors, then you can view the Aztec diamond as being the subgraph that you get from the infinite grid of alternating black and white vertices when you cut it off with suitable bounding lines. So here you should think of each of these bounding lines as determining a half plane. And we're intersecting these half planes to get a finite region and the associated induced subgraph of the infinite square grid. And a feature of these boundaries is that they segregate the colors, so that if you were to look at extending this picture, we'd see a lot of black vertices on one side of this dividing line and a lot of white vertices on the other side. So we're sort of trying to thwart the existence of a perfect matching by basically making a big color imbalance at the boundary. So that is the design principle that I use when thinking about how to come up with an analog of Aztec diamonds for trimer covers of the infinite grid of triangles, the 6 regular graph. So in that picture, let's draw this picture. we really need 3 colors. And I don't want to take the time to reset my pen all the time. So maybe I'll use, oh, I know what I'll do. I'll use a dot in the middle. Yeah. So my 3 colors will be black, white, and dot in the middle. And so my coloring is that each white vertex has only black and dotted neighbors. So let's see, they'll alternate because it's going to be a proper 3 coloring. And each black vertex is only going to have white and dotted neighbors. And each white vertex, each dotted vertex is only going to have white and black neighbors. So this is the sort of 3 coloring that I have in mind. And the sort of Conway and Lagarias boundary condition was to cut off the infinite 3-colored lattice with lines that look like this. But these lines don't thwart the existence of trimer covers. They kind of help you because they're ensuring that your finite region has a nice equal balance between the 3 colors, because you can even see along each side of this dividing line, we see all 3 colors appearing. So what I'm going to do instead is use dividing lines that look like this. So if you were to continue it, you'd see that butting up against that dividing line on the left are just dotted vertices, and butting up against it on the right are just white vertices. So again, we're enforcing as much chromatic separation as we can. So that means that if we have a region like this that can be tiled with trimers, we expect it to be very constrained along the boundary, and perhaps even to be statistically frozen in the sense that nearly all of the trimer covers will have a very specific arrangement of trimers near the boundary, in analogy with domino tilings of Aztec diamonds. By the way, I apologize that I'm looking off to the side. I know I must look very shifty and suspicious or shy, but it's just that I'm giving the presentation on my iPad, but maybe I can put my iPad up here, and then I'm looking more at you while I'm talking. So anyway, these are the sort of half planes I looked at, and ways you could arrange 3 or 6 half planes symmetrically. The symmetry matters because if we have threefold rotational symmetry about this kind of a center, so here's the center point that I'm going to use. If we have threefold rotational symmetry about such a center, then chromatic balance globally will be assured. You might want to think about Aztec diamonds for a second, which do have this sort of center, if you look at them as graphs, composed of a 4-cycle of 2 black nodes and 2 white nodes. And the Aztec diamond graph has a rotational symmetry of 90 degrees that exchanges the 2 color classes, so it's guaranteed to have equal numbers of black and white vertices, and around 43 after. Okay, I will aim for that. But meanwhile, having the kind of boundary that you have, sometimes called domain wall boundaries, I would appreciate, by the way, if someone could give me a rigorous definition or semi-rigorous definition of what domain wall boundary conditions mean. And I guess I should digress here and say that alternating sign matrices, which were a great source of intrigue and frustration to combinatorialists, turned out to also be related to theoretical physics by way of the 6-vertex model. And the boundary conditions for alternating sign matrices, viewed as being states of the 6-vertex model, also have this characteristic that the boundary conditions are about as tight as they could be without entirely forbidding the existence of states at all. So again, they're going to exhibit this kind of tightness around the boundary, which constrains their behavior there and leads to this sort of behavior where you have rigidity near the boundary, and the boundary makes its influence felt pretty far into the bulk inside. So there's a long tradition of combinatorially fruitful specializations of statistical mechanical models where the specific boundary conditions that make them amenable to combinatorial techniques and to exact solvability seem to be related to giving boundary conditions that challenge the model to have any states at all, but still allow states to exist. So you can have half planes that are sort of defined by numbers that express the displacement between the bounding line and the center point, where I remind you the center point is not one of the vertices. The center point is at the center of a triangle. And we're actually going to have only three parameters. Actually, only two parameters. I'm going to be looking at intersections of 6 half planes around this center with 6 different orientations. But because I want these boundary conditions to have threefold rotational symmetry that interchanges the color classes cyclically and therefore guarantees equal numbers of black, white, and dotted vertices, I'm actually going to require that these 6 displacements are actually only 2 displacements repeated cyclically. So I could call them R and S, and then the pattern of displacements will be R, S, R, S, R, S. So being very schematic here, I'm going to have something that looks like this. So here are those displacement vectors for those half planes. It's kind of a crude drawing, but you'll see sort of long, short, long, short, long, short if you look at those displacement vectors. So here I'm going to completely drop showing you pictures and show you text. It's going to be the text of an email I sent out to people in an online forum called the Domino Forum. And if any of you want to keep up with what I hope is going to happen in the next few years with this inquiry, then you should subscribe to the Domino Forum, because long before there are any publications, that's the place where I find a lot of collaborators and do a lot of work on this kind of stuff, as you'll see. So here's an email I sent out to Domino. Okay. I've used David Desjardins' tiling count program to enumerate certain kinds of polyhex tilings in the hexagonal grid. Specifically, I've looked at trihex tilings involving 2 kinds of trihexes considered by Conway and Lagarias in their article Tiling with Polyominoes and Combinatorial Group Theory, which I call stones and bones. A stone, okay, I notice here I'm using the tilings picture. So there's this duality between looking at tilings of regions and looking at dimer or trimer covers of regions, where you replace faces by vertices and vertices by faces, and edges become perpendicular edges. So I hope most of you are familiar with that kind of game in statistical mechanics models relating like dimer covers with domino tilings and things like that. A stone consists of 3 mutually adjacent hexagons, or in the picture I drew before, 3 mutually adjacent vertices in the triangular graph. A bone consists of 3 hexagons whose centers are collinear, with 1 hexagon adjacent to the other 2. The third kind of trihex, which I used to call a bend and now call a phone, is disallowed. And I'll skip the next paragraph, but there is some confusion in the literature about nomenclature, which I took as an invitation to invent my own. 3 color the hexagons, or for us the vertices, so that no adjoining 2 vertices of the same color. Under this coloring, each bone or stone must contain 1 vertex of each color. By the way, that's one reason I've eliminated these phone primers from consideration. They seem to mess up the exact enumeration properties, and I think that's related to the fact that they are not representing each color class fairly. Consequently, a region in the grid can be tiled by stones and bones if and only if it contains equally many vertices from each color class. The regions I consider admit 120-degree rotational symmetry about a point where 3 hexagons meet, or in dual language, in the center of one of the triangles. Such a region automatically satisfies the color balance condition. We index hexagons. Let's not worry about indexing them. Let's just say that I use the indexing to define the intersection of these 6 half planes in the grid. So for positive integers a and b, let h of a, b be the union of, be the set of the vertices indexed by triples that satisfy certain inequalities, and let n of a, b be the number of bones and stones tilings of HAB. I should alert you here that I've subsequently found that this indexing is wrong because the combinatorial formulas are nicer if you re-index. So A and B are off by 1 in the way I've defined them. But anyway, here are the sort of numbers I get. So this is the unconstrained case where I'm allowing all stones and bones. Later on, I'll talk about what happens when you restrict. So property A, I think, is easy. So there's symmetry between A and B, and that's just because these two regions are mirror images of one another. By the way, a point I haven't written here and stressed, but I realize is important for later on, is to say that these regions do not have mirror symmetry. They have a kind of a spiral. They have a rotational symmetry, but they do not have reflection symmetry. I'll skip conjectures B and C because enumeration is not so interesting when there's only one tiling, although it's important to understand that. I want to intrigue you, so let me focus on more interesting enumerative results. So here is something that I think is really interesting, which is this kind of two-adic continuity. So here I should back up and say that what I mean expressed in abstract language is that a certain function of the integers admits an extension to the two-adic integers, which is not normally true for non-polynomial functions. But what this means, if you're not familiar with the two-adic numbers, is that this function of A, S of A, which I've defined as the number of these trimer configurations, trimer packings, when these two offsets A and B satisfy a certain relationship, namely B is equal to 2A minus 2. Which is that if you know what A is modulo every power of 2, you know what S of A is modulo every power of 2. So specifically, if you look at the parity, if you look at S of A mod 2, you get a sequence of zeros and ones. That sequence is periodic mod 2. And if you look at it mod 4, S of A mod 4, well, it's always 2 mod 4. Conjecture D3 says, if you look at S of A mod 8, that behavior is determined by whether A is odd or even. So the behavior of S of A mod 8 is determined by A mod 2. If you want to know what S of A is mod 16, that only depends on what A is mod 8, etc. And so that's the sequence S of A. There's another sequence, T of A, which is defined by looking at the number of these dimer covers when B is equal to 2A minus 3. So it also seems to satisfy this two-adic continuity property. So this is kind of unusual. And if you look through the literature for similar two-adic continuity properties, intriguingly, one of the first hits you'll find is Henry Cohn's article on two-adic continuity for dimer covers. So if you look at the number of dimer covers of an n by n square grid where n is even, this function of n does satisfy this two-adic continuity property. But the way it was proved is to use facts about determinants and the fact that there's this beautiful temporally way of viewing, well, actually, who was due to originally? I'm blanking on this. These matrices. Can someone help me out here? Who figured out that the dimer model is actually a Pfaffian model and a determinant model? I'm just blanking on the name. Castellane. Yes, it's Castellane. So using Castellane's method and all kinds of things that flowed out of that, you can express lots of enumerative properties of the dimer model in terms of determinants. But here we don't have determinant formulas for trimer covers, so I have no idea why this should be true. But this is certainly one intriguing indication that there's something going on here that combinatorialists should want to understand, and I'm hoping physicists can help. So let me mention here that these conjectures wouldn't have been possible without computations using a program by David Desjardins. If you want to use this kind of program, let me tell you what it can do. You give it as input a description of a region. So here we have a picture of a region expressed in terms of empty cells, which are represented by dots, and X's, which are cells that we want to include in the region. And below that, you have a bunch of allowed tiles. So one tile is this vertical tile, another is this horizontal tile, another is this diagonal tile. And these correspond to the three different bones where we've sort of distorted things to fit them in a square grid. So the three different orientations of bones become horizontal, vertical, and diagonal. And then these are the two stones. And I apologize that this is not done with fixed width font, so you can't really see that it's a grid. But this bone, for instance, really is intended to be something more like this. So this is a sort of convenient ASCII way to describe tiles, or more properly prototiles. They can be translated at will, and trying to find all the ways to fill up some larger region with these sorts of tiles. I gather that someone else wrote a program to do this. I don't know if David's is faster than theirs or not. I believe this other program exists in Sage, but I forget the details. But anyway, it would be good for people to make these things public so that other people can make use of them. So that's the unconstrained case. I want to finish now by talking about these other interesting combinatorial observations we make when we restrict the tiles. There's this nice product formula that David Desjardins was actually the first one to find. I'll come back to that when I get to the all results file. Okay, so if we forbid bones and allow all possible stones, remember we have these two offset variables, which I was calling A and B. So if we forbid bones entirely, we get just regions that can't be tiled and regions that can be tiled. If we allow one kind of bone and one kind of stone, actually, let me just back off a step. What kinds of interesting subsets of the prototile set might we look at? So I want to remind you that the allowed tiles are two orientations of these things that I call stones, which are triangles, which can either point up or point down. And these three different orientations of these three in a line tiles that I call bones, which emit three orientations. So we have a tile set of size 5. And so you might think there are 32 different subsets of those prototiles we might want to allow. Of course, the empty subset is not interesting, but that still leaves 31 classes of tilings. But then you might think, well, wait, some of them are related by symmetry. So we can really whittle down that set of 31 tiling problems or prototile sets to something smaller. And in fact, you can whittle it down to 11. And one observation that's related to that is if you know how many different kinds of bones you're allowing, 0, 1, or 2. Sorry, 0, 1, 2, or 3. And if you know how many of the two different stones you're allowed to use, namely 0, 1, or 2, that really determines up to symmetry your prototile set. And that's because the symmetries of stones already have twofold rotational symmetry, but not threefold rotational symmetry. Whereas the bones, did I say this wrong? The set of bones, there are 3 sets of bones related by 120-degree rotations. There are 2 kinds of stones, each of which is a 180-degree rotation of each other. There's a kind of incompatibility between those 2 forms of symmetry. And that means that if you know how many stones you want to allow and how many bones you want to allow, that really determines the problem up to symmetry. So you just need to say for, how many bones do you want to allow? 0, 1, 2, or all 3 of the different kinds of bones that are allowed. That's 4 possible numbers. And how many of the stones, the stone types, do you want to allow? 0, 1, or 2. That's 3 possibilities. 4 times 3 is 12, so there are only 12 cases, and one of them is trivial, namely allowing no tiles at all, so there are really only 11 cases to look at. So it's really easy with David's program to just modify the input file by crossing out one of the prototile types, just deleting the lines associated with it, and feeding it to the program and letting it do its thing. So if we forbid all bones, we get very predictable results, just zeros and ones. If you allow one type of bone and one type of stone, turns out there are no tilings at all, except when a equals b equals 3. And that's the very earliest case I showed you. Remember when I drew that triangle graph with 6 vertices, and I had it tiled by a 3 in a line tile and by a 3 in a triangle tile with 1 bone and 1 stone? Well, that's the only case that you can tile in these shapes that I have described for you, but I have not given a name to yet. But if you consider those regions defined by those 2 parameters, then it turns out that the only case in which you can get a tiling at all is the case that I showed you a picture of. And things are not that much more interesting when you allow 1 kind of bone and 2 kinds of stones. There's always 1 tiling allowed, or 2 kinds of bones and no stones at all. That's never possible. But as we increase the number of prototiles that we're allowing, things become recognizably like, the kinds of sequences you see in OEIS in Stanley's book on enumerative combinatorics. So if we allow 2 kinds of bones and 1 kind of stone, then we start to see numbers that look like this, surrounded by a whole lot of zeros. So there's a lot of rigidity to which of these regions you can tile and which you can't. But when you can tile it, there's a nice combinatorial structure. It's a double factorial. It's 2 times 4 times 6 times ... times 2n. So it's just on the borderline between being so complicated that we can't hope to solve it and being so simple that we must feel as respectable combinatorialists, we must be able to understand the structure of these tilings in such a way that we can prove that this product formula works. So here, let me reveal what my proposed terminology is for the regions that I want to tile. I'm calling them benzels. And I doubt anyone has given them a name because they really look ungainly. The only way you would contrive such a region is if you had some idea in mind, like trying to have this chromatic separation at the boundaries. And I call them benzels for 4 reasons. First of all, this is a fun word from a science fiction novel that I like, Contact by Carl Sagan. Benzel was also the inventor of the merry-go-round, and these regions have this nice rotational symmetry, which is the only nice symmetry they have. The Mercedes-Benz logo has this nice little junction where hexagons meet. And also benzene has this nice feature, which is also reminiscent of this model. So I'm looking at trimer covers of benzels. That's the name of the game. So suppose you allow 2 bones and 2 stones. So then you get these numbers in this diagram. I'll remind you again that there's 2 parameters here. And so you can make a 2-dimensional table showing how many tilings there are as these parameters vary. If the parameters are too disparate, if one of them is more than twice the other, then we seem to get uniqueness of tiling, but you get genuine variety when you stay close to the diagonal band where the 2 parameters of translation seem to be, are close to each other. And we get these numbers with these nice small prime factors. And in one of these cases, we get something called the large Schroeder numbers. And in other cases, we get these numbers that have these kind of small prime factors. And so I couldn't find a governing formula, but they seemed too nice to not be given by product formulas. So at this point, I wrote to the Domino forum and I said, hey, can we find formulas for these numbers? Oh, that's the wrong file. Let me show David Desjardins doing some enlightened pattern finding, showed that the sequence, if you look at its second divided difference, so it's the k plus second term times the kth term divided by the square of the k plus first term, was given by 256 times this, rational function of k with, I forget what the degree of the numerator and denominator are, 5 or 7 or something like that. A real, tour de force of inferring from data a pattern. And some people challenged it as being underpowered. So I generated another term and it still fit the pattern. So at this point, there's very little doubt that this is the right formula, but we don't have a proof for it. But it's very much like plane partition formulas. The growth rate is quadratic exponential. So it's sort of like a double or a product. It's a big product. It's a big number, but it's in the kind of ballpark of, 20th and 21st century combinatorial exact enumeration. So there should be a way to prove this. So I've taken us as far as 2 bones and 2 stones, where we now have an exact conjectural formula but no proof. Then I already mentioned that if we allow unconstrained tilings, we don't get any kind of nice exact formula. Maybe I didn't stress that. We don't, but we get this bizarre two-adic continuity property, which really cries out for explanation. Then, going in the other direction, what if we forbid stones entirely? Which I'm not sure this is going entirely in the other direction, but this is an especially interesting case. This is the one Conway and Lagarias would have, I think Conway would have really liked, which is, suppose we forbid stones entirely and we allow bones, so tribones. So it's exactly like one of the problems that Conway and Lagarias considered in their article. It's a pure tiling that just allows these tribones. But instead of allowing these sort of natural triangular regions, we have these benzyl regions. Suppose we try to tile those. Then we find there's a very sparse set of tiling of parameter values R and S, or A and B, I guess I call them here, that admit. Actually, I think this was written after I'd switched over to R and S coordinates, the R and S parameterization of benzyls. So does anyone recognize, here's another pair, 1, 2, 5, 7, 12, 15. Does any combinatorialists in the audience recognize this sequence of numbers? So it's often split up as 2 different sequences.
Catalan.
Sorry?
Catalan?
Catalan numbers. Oh, yeah, they begin 1, 2, 5. Sorry, 1, 2, 7. No, sorry, 1, 2, 5, 14. So no, these are not Catalan numbers. They're much more slowly growing. In fact, these sequences grow quadratically. Euler loved these numbers.
You mean this eta function? Or?
Well, they are related to the eta function. They come up in connection with partitions and the eta function and all that. Euler proved this thing called the pentagonal number theorem, in which he showed that a certain product, well, specifically the product 1 minus x to the n, product as n equals 1 to infinity, has almost all terms vanishing, except when the exponent of x is a pentagonal number. It's one of these numbers, 1, 2, 5, 7, 12, or 15. So in a similar way, the number of tilings of a benzyl by stones and bones, where no stones are allowed, so bones only, vanishes, except when these R and S parameters are 2 consecutive pentagonal numbers of the first kind and of the second kind, respectively. So there's this quadratic parameterization of R and S. And if R and S happen to lie in this very sparse family of benzyls given by a single parameter n, where R and S are both quadratic functions of n, then the number of tilings is non-zero. But other than that, it's 0. I should say, by the way, that for this case, I have an idea of how to prove that result. You would use Conway and Lagarias' combinatorial group theory approach to show that certain tiling invariants that need to vanish if tileability is possible don't vanish unless these conditions are satisfied. So this is vaguely similar to the main result of Conway and Lagarias' paper, except there what they do is they show that if a certain parameter doesn't lie in certain congruence classes, then no tiling is possible. So it's sort of a linearly sparse set, whereas this is a much sparser set of parameter values, but I believe you can use it using the combinatorial group theory approach, at least to characterize those values of R and S for which a tiling exists. But that's not going to necessarily tell you how many there are. And in fact, I was not able to find a nice pattern for the number of tilings in those cases where I'll call them pentagonal benzyls. So for pentagonal benzyls where R and S are given by pentagonal numbers, I don't have any idea of what the formula is for the number of tilings, but it certainly is intriguing that these things only exist for pentagonal numbers.
Yeah, Jim. Thank
Yeah.
you for this very interesting improvised conference and the results and the experimental mathematics. It is what we praise. But due to the shift, you have 3 minutes left.
Okay.
Sorry.
So I will finish quickly, and I'll say that in the case of 3 bones and 1 stone, I don't know anything. So that's really all I have to share in terms of intriguing results. The last thing I want to say is that I will be presenting a version of this talk, hopefully with many more pictures and perhaps some results, at the OPAC conference coming up in May. That's Open Problems in Algebraic Combinatorics. So if you want to hear more about this stuff, you should attend the OPAC conference in May and contact the participants. And that's really all I have to say. So thank you for listening, and I'll take any questions or suggestions now. And I'll also say that I have trouble reading physics articles. So I know there are good ideas about trimer models there because people have integral formulas for entropy and things like that. I just don't understand the methods. So if any of you feel like you understand that literature and have any mathematician-friendly comments to offer about how to read those articles, I'd be very grateful. Thank you for attending.
Thank you for having so nicely been available. Are there questions, remarks, comments? So thank you again, dear Jim. Thank you for your talk.
For 10 minutes.
Yes. Cyril Banderier says something. Many of your sequences are algebraic. You want to answer something? Do you want to answer?
Oh, Cyril had a question. I'm sorry, I didn't see that before. Cyril asks, many of your sequences are algebraic generating functions. Do you know one which is not? Yeah, I do not know off the top of my head which are not. But I should also say, anyone who wants to get copies of like my emails from the past to the Domino Forum, the documents you already saw, or my file of results, I would be happy to email them to you, so just contact me by email. I'm jamespropp@gmail.com. And I can handle Cyril's question and others offline.
Thank you.
Thank you.
Sometimes.